All right, so we're going to review some chapter 24 stuff. I'm going to do some carbohydrate chemistry first. All right, so your carbohydrates, that is some number of carbons with some number of waters. All right, so the ones that you have to know, there were three of them that you had to know. You have to know D-glucose. All right, you have your 4 chiral carbons on your D-glucose. Again, D because the OH on the last chiral carbon is on the right, so this is your D-glucose. All right, so if I wanted a different, and this is a aldo hexose, this is an aldehyde, so it's an aldo hexose, hex because there are 6 carbons, so glucose, the formula for glucose, the molecular formula is C6H12O6. And so if you look at it in terms of a carbohydrate, it is 6 carbons and it is also 6 waters. All right, so you have 6 carbons, 6 waters. That's the molecular formula for D-glucose, which is an aldohexose. You have the exact same molecular formula for D-fructose. Right, except D-fructose has, it's a ketose, so it has a ketone group, and it has then 3 chiral carbons. All right, and so the remaining 3 chiral carbons have the exact same configuration as the bottom 3 for D-glucose. All right, so this is D-fructose. All right, and this has a ketone group, so this is a ketone. And again, it's still 6, so it's still a hexose. So this is a ketone because now you have a ketone group, and it is hexose because there are 6 carbons. And then the last one that you were to memorize was ribose. Ribose is also a D-ribose. All the naturally occurring sugars are the D class of sugars. All right, and so it has 3 chiral carbons. So this is D-ribose. All right, and so that is a aldo because it has the aldehyde functional group, and it has 5 carbons. It is a pentose. So that is a C5H. We can add them up. 2, 4, 6, 7, 8, 9, 10. H10 O's. Add them up. 1, 2, 3, 4, 5. And so that is a carbohydrate with the formula of 5 carbons and 5 waters. So that is your D-ribose. So those are the ones that you were to memorize. D-mannose, if you were to have D-mannose, it would tell you that D-mannose is the C2 epimer of D-glucose. All right, so D-glucose you have memorized. It is right here. And so we number it from the end closest to the C double bond O. So this is carbon number 2. Epimer means just change the stereochemistry at carbon 2. So that would mean that your OH would be on the other side and your H would be, they would just switch. Your OH and your H would switch sides only at carbon 2. The other carbons would all remain the same. All right, so if it says the C2 epimer, that just means switch your H and your OH on carbon number 2, and then you have D-mannose. You don't memorize D-mannose, but you have to know what an epimer is. That means you switch your H and your OH, and the problem will tell you at what carbon that you're going to do that on. Okay. If you take your D-glucose, and you can do two things with your D-glucose, two reactions that you will need to know. All right, so you can take your D-glucose, all right, so D-glucose. All right, the reaction is always going to occur at our aldehyde for our D-glucose, and so you can oxidize it. If you are going to oxidize your D-glucose, your aldehyde is going to gain an oxygen and become a carboxylic acid. The remaining stays the same, so I'll just put R. That is not changing. All right, so I'm circling what we're looking at. The aldehyde oxidized is now a carboxylic acid. You can reduce it, H in brackets. If you reduce it, then your aldehyde is reduced to a primary alcohol. All right, and so again, the remaining part is the same. So this is simply the R. This part is R. This part's not changing. All right, and so if you reduce it, as shown by H in brackets, all right, so that is then the addition of hydrogen for a reduction. All right, so you have added hydrogen to reduce that. Or, of course, you could lose oxygen for a reduction as well. Oxygen, you can gain oxygen, or you can lose hydrogen. Here we gained oxygen. Now this carbon is bonded to two oxygens, and it has been oxidized from an aldehyde to a carboxylic acid. All right, and so we'll talk about reducing sugars. All right, so reducing sugars are oxidized. All right, so if we are doing this reaction and it has been oxidized, so this would be the oxidation half reaction. Remember, the reactant of your oxidation half reaction is the reducing agent. All right, and when your reducing agent is a sugar, it would then be called a reducing sugar. And so when you oxidize, if your sugar is able to be oxidized, it is a reducing sugar. It is a reducing agent. All right, so when you talk about reducing sugars, you know that that is talking about a reducing agent. That's a very common thing to be called as a sugar, a reducing sugar. All right, other things to do with the carbohydrates. That's pretty much what you need to know for the carbohydrates. All right, so let's do some problems out of the homework. We're going to look at amino acids. (2434). All right, so it says draw this amino acid at a neutral pH. So we have our amino acid. I like to write it with the NH2 on the left, and then my R group coming off of this position, which is a CH, CH3. It's not how they wrote it. This is how all of your amino acids should be written. Your amino acid should be written with the nitrogen on the left and the carboxylic acid on the right. That is by convention. Nitrogen's on the left, carboxylic acids are on the right. Just like your glucose, you would put your carbon double bond O at the top end of your Fisher projection. All right, so this is your side chain. So this is a side chain only containing carbon and hydrogen. That makes it nonpolar. All right, and so if you are nonpolar, then you are also neutral. Every nonpolar side chain is going to be a neutral amino acid. Now, neutral amino acids have a charge of 0 at pH equal to 6. And so that's called the isoelectric point. That is when it is neutral, no charge. All right, but it said to put it in its Zwitterion form. So that is the thing about amino acids, because we know that of course, acid is very acidic, the most acidic organic functional group, and the amines are the most basic organic functional group. And so what it does is an internal acid-base reaction where the base takes the proton, the H plus, and the acid donates the H plus, and so you're left with NH3 that has a charge of +1, and you have your C double bond O with your O with a minus charge after it loses the H. So a neutral amino acid can be written with all the formal charges of 0, as shown first, or you can show the Zwitterion form, where you show the positive nitrogen and the negative oxygen. All right. Now, if we change the pH, because this is what it looks like at pH equals 6, if we make this acidic, all right, so I want to make it at pH equals to 3. So if my pH is 3, that means I threw in some HCl, some acid, H plus. All right, and this acid is going to put the H back on the carboxylic acid. So the NH3 remains positive, but now our negative oxygen is going to be neutral, because we are going to put our H plus on the O minus. All right, and so now the overall charge here is +1. So in acid, you're going to have a positive charge. In base, if we add hydroxide, OH minus, it's going to pull off the hydrogen. And the acidic hydrogen is right here on the NH3 plus. And so that's going to become NH2. And then CH, the R group, C double bond O, and O minus. And so when you are at a pH equals 9, all right, so pH 3, this is acid. pH 9, this is base. When you put it in base, it's going to have a charge of -1. All right, so your isoelectric point, your pH, where your amino acids are neutral for your neutral amino acids, is at a pH of 6, because the carboxylic acid is more acidic than the amine is basic. And so the neutral point, the isoelectric point, is slightly acidic at pH of 6. All right, there are 15 neutral amino acids. There are 2 acidic amino acids. And there are 3 basic amino acids. Now, the neutral amino acids, they are neutral at pH equals 6. Your acidic amino acids are neutral at pH equals 3. Your basic amino acids are neutral when the pH is equal to 9. So you should know the 2 acidic amino acids, glutamic acid, aspartic acid, and you should know your 3 basic amino acids, and the rest of them are all neutral amino acids. All right, let's do, let's say I have a DNA sequence. Here's my DNA. A, T, C, G, C, A, T, C, G. All right, so there's my DNA. And so now I'm going to make a messenger RNA from this strand of DNA. So remember, your DNA has thymine, your RNA has uracil. So your DNA base pairs, A, 2 hydrogen bonds to thymine, A to T, C, 3 hydrogen bonds to G. But when you're looking at your RNA, it is A, 2 hydrogen bonds to U, uracil, and C, the same, 3 to G. All right, so when you have your base pair for DNA is A. To RNA, it is not T. There's no T in RNA. It is U. All right, and so the T would go to A, and C goes to G. G goes to C. C goes to G. We're just doing the base pairs. A does not go to T because T is not in RNA. It is U, T to A, C, G, G, C. All right, so there's your messenger RNA, and this is your codons. All right, so now it's going to ask for the transfer RNA. All right, this is your anticodons. All right, so U, so we're over here, base pairs. U goes to A goes to U, G goes to C. C goes to G, G goes to C, U goes to A. A goes to U, G goes to C, and C goes to G. So you're just doing your base pairs. Remember, for your RNAs, you have U. For the DNA, you have T. All right, so then it's going to say, give the amino acids. All right. You have to know that you're looking at the codons. Okay, the biggest mistake, the most common mistake is that people will look at the anticodons, the transfer RNA. And I understand that because that's what's bringing in the amino acid, but they have the anticodons. The chart is a codon chart. So UAG, when you go to the chart, UAG, wrong chart, we go to the chart, UAG, so UA, and then you find UAG. Well, that is a randomly put in there. That is the stop codon. So that's why you don't just make stuff up, because then sometimes it doesn't quite work right. All right, so what we know is that in this one, this ended a previous protein synthesis. All right, and so this is just a how you do it, not an actual problem that is real. This is a made up problem. All right, so your RNA, next one is CGU. CGU is arginine. All right, so we would have arginine as our next amino acid. And then AGC. So AGC is serine. All right, now if you looked at the anticodons, you would have different amino acids and not the answer. All right, that chart is a codon chart. The chart you're going to be given on the test is a codon chart. I will never give you an anticodon chart. It will always be a codon chart. You're looking at the messenger RNA, not the transfer RNA. The transfer RNA is bringing in the amino acid, but it's bringing it in with the anticodons. All right, so the anticodons are from the transfer RNA, the codons are from the messenger RNA. The chart is a codon chart. Make sure you're looking at the messenger RNA codons, not the transfer RNA anticodons, to find your amino acids. Let's do 2453. There's an error with 2453 because the problem says write the structural formula of the addition polymer made from trans 1,2-dichloroethene. And then they give you the formula for cis. I don't know if it's a trick or if it's just an error. I think it's just an error. But in the problem, the name says trans. And then they wrote the cis. Right? So I'm going with, they want the actual question, says write the structural formula of the addition polymer made from trans 1,2-dichloroethene. And then they drew a structure of cis. For some reason, they did not draw a trans. All right, so you have an alkene. Alkenes do addition reactions. And so this is going to be an addition polymer. When you have an addition polymer, your double bond, the pi bond, you break, sigma bonds all remain. Carbon has to have 4 bonds. And so the extra bond when you break the double bond is going to be the polymer, so it just keeps going. So the next C is HCl, then ClH, and it keeps going and going and going. You keep repeating that same monomer. So this is the monomer, and this is the polymer. All right, and so when you name it, this is trans 1,2-dichloroethene. All right, so to name it, it's really easy but different, strange, because to name it, you simply put the word poly in front of the monomer. Now, the problem with that is you have a poly and then trans 1,2-dichloroethene. All right, so the problem with that is, of course, the name. It ends in -ene, but it's not an alkene. It's, of course, a polymer because it starts with poly. All right, and so note that the way you name a polymer is simply to put the word poly in front of the monomer name for your addition polymers. And so your poly trans 1,2-dichloroethene, although it says ethene, there are no double bonds. It just says that is the monomer that we made this polymer from. All right, let's do the Kevlar. Kevlar is interesting. So 24.55, that is Kevlar. All right, so this is a condensation polymer. So the addition polymers are the ones that you start with an alkene. If you're not starting with an alkene, you have a condensation polymer. All right, so they give C double bond O, then they have a benzene ring with another C double bond O, and then that is connected to an NH, and that is another benzene, another NH, then a CO, then a benzene, and then a CO, and an H, then a benzene, and H. And, all right, so that's what they have written in the book. All right, so this is a polyamide. All right, so all of your proteins are polyamides. All of your peptides are polyamides. All polyamides are not peptides. This is a polyamide, and this is not a polypeptide. This is not a protein. This is Kevlar, right? So what we do is we're going to do a hydrolysis. We're going to split it with water. So we split the amide bond with water. The C double bond O is going to get the OH of water. The N is going to get the H of water. All right, so anytime you see an amide functional group, you're going to split it with water, hydrolysis. All right, so you have your OH for your C double bond O, your N gets the H. Anytime you see an amide, you split that with water. The OH goes to the C double bond O, the H goes to the N. All right, and now we see our two monomers. Our two monomers to make Kevlar are this diamine with a benzene ring in the middle and our dicarboxylic acid with a benzene ring in the middle. And so to make this Kevlar, you will need these two monomers. All right, so you need your NH2 and then a benzene ring in the middle, and then another NH2. You will also need a carboxylic acid with a benzene ring, and then on the other side, another carboxylic acid. All right, so you'll need a lot of those, you'll need a lot of those, and then when you polymerize it, you will get your Kevlar, which is the polymer that they showed there. Now, again, what you're going to do is you're going to lasso water. You're going to take the H off of your NH2, you're going to take the OH off of your carboxylic acid, and that is your polymer. So you take the H off of your NH, you take the OH off of your carboxylic acid. And that is the polymer. You would, the example up here, it gave it multiple times. You just have to find the repeating unit and then put the N. That's the repeating unit, and you put the N. 57 is a good example of things that you need to know. 24.57, which the following amino acids have a non-polar side chain. And so the R group for the first one was your methionine, CH3, S, CH2, CH3. All right, CH2, CH2, that's the R group. And so here, we do not have just hydrocarbons, we have a sulfur. And the sulfur that is between two carbons is non-polar. The second example also has sulfur, but this R group has a H with the S and then CH2. All right, so the SH, that is a polar. All right, so remember your nonpolars, there are about equal amounts of polar and nonpolar. But if you have only carbons and hydrogens for your side chain, then it's going to be nonpolar. That would not answer this question. If you have an O in the R, and so if there's an oxygen anywhere in your side chain, then it's polar. All right, so that one didn't have an O. All right, so this takes care of most of your nonpolars. This takes care of most of your polars, but not all of them. So you need to know which R groups are polar and which ones are nonpolar. All right, so that then gives us to the next problem, which was 58. The R groups here, we have an amine. All right, so the amine group, that means it's going to be basic. All right, so this is actually a basic amino acid, and of course that's polar. If you are acidic or basic, you are definitely polar. And then the next R group that they give is just a bunch of carbons and hydrogens, CH3, CH, CH3, CH2. So that is only carbons and hydrogens, therefore non-polar. So when your side chain only contains carbons and hydrogens, it is a non-polar side chain. All right, let's go to 2472. All right, so this one is a good review also for the final because we're going to do an empirical formula. All right, so we have a polymer. The polymer is NH2, and in the middle, some number of CH2s. All right, so we have NH2s at each end. We have a diamine. All right, and then we have a dicarboxylic acid with 8 CH2s in the middle. So we have a carboxylic acid. So this is very similar to our Kevlar. CH2, except the Kevlar had benzene rings in the middle. This just has CH2s in the middle. but the chemistry is very similar because we have diamines and dicarboxylic acids, and we're going to lasso water. All right, so when we lasso the water, it's the H from the NH2 and the OH from your carboxylic acid. So it's exactly the same as we did before, except again, these are CH2s, but we don't know how many CH2s are between my nitrogens. All right, so you're going to lasso water. So your OH from your carboxylic acid and the H from the NH2, so one of those H's. So we don't ever put that, but of course we're going to get N number of waters. So it's a condensation. We lasso water. Water is kicked out of that reaction. All right, so the question is, how many carbons are between my two nitrogens? In order to find that, we have done a elemental analysis, and we have percentages. Anytime I have percentages, I always assume a 100-gram sample. And I do that because then all of my percentages become grams. If I have 100 grams and 66.1% is carbon, well, then that means 66.1 grams are carbon. And so I divide that by the molar mass, 12.01 grams per mole. Then I take my 10.3% of hydrogen, and if I have a 100-gram sample, that is 10.3 grams of hydrogen divided by the molar mass, 1.01 grams per mole. If I have 11% nitrogen, 100-gram sample, I have 11 grams of nitrogen, and I divide that by the molar mass. And finally, I have 12.6% oxygen, so I have 12.6 grams of oxygen divided by that molar mass, which is 16 grams per mole for oxygen. All right, so now I convert all of my masses into moles by dividing by the molar mass. And so I get my numbers. All right, so 5.5, 10.3, 0.78, 0.78. All right, so when you're doing this, so you got to go to moles, and then you got to remember that you're going to divide by the smaller number. So the smallest number here is 0.78, 0.78, 0.78, 0.78. That's your smallest number. All right. And so in this case, we get integers. And so we get 7 moles carbon. We get 13 moles hydrogen. We get 1 mole nitrogen, and we get 1 mole oxygen. And so we have our empirical formula. Our empirical formula is C7H13NO. So that is the empirical formula. All right, but when you look at your polymer, you have 2 nitrogens in your polymer, and you have 2 oxygens in your polymer. All right, and so you have to multiply your empirical formula by 2 to get 2 nitrogens and 2 oxygens. And so that is C14H26N2O2. So there's my 2 N's, there's my 2 O's. Now I have to have 14 carbons. I count my carbons. Right here, I have 10 carbons. We have the 2 C's and the C double bond O's plus the 8 CH2s. So I have 10 carbons here. All right, in order to get 14, now I know that this value here has to be 4. All right, because I have 10 carbons here, I have to have 4 carbons here in order to get 14 carbons. All right, and if I do that, now I know I have my 2 N's, I have my 2 O's. You will want to check to make sure you have 26 hydrogens. All right, so we have 8 times 2, we have 16 hydrogens here. And now we have 4 times 2, we have 8 hydrogens there. All right, but that is not enough. That is 24. But you see that we have another hydrogen here and here. That is 26 hydrogens. And so that is your formula. And that tells us that 4 is the answer to the question. It is NH and then CH2 sub 4, NH. All right, 2474. All right, so they're not writing it the way I like to write it. I'm going to write it the way it should be written. Always have the N on the left, and then you have your chiral carbon, then you have your R group, and the R group here is a CH2, C double bond O, OH. That is your aspartic acid. That's one of your acidic amino acids. Then you got your C double bond O, then your NH, and then your CH. And the R group on this one is your phenylalanine, CH2 with the benzene ring. And then you have your C double bond O, and then this is an O, CH3. This is aspartame. All right, that is the methyl ester of a dipeptide. All right, so the dipeptide here was an OH, and then that reacted with methanol. All right, and so you lassoed the water, and then you have your OCH3 that comes on. All right, so that is the methyl ester of your dipeptide. All right, and so we want to react it with water. We're going to hydrolyze it. We're going to split it using water. All right, so you have your amide. All right, this is 2 amino acids. So this is a peptide bond. Your amide bond is a peptide bond when you are combining 2 amino acids. All right, and so what we're going to do is we're going to hydrolyze it. We're going to split it. Remember, your OH goes to the C double bond O, and your H goes to the nitrogen. Now, when we hydrolyze that, we also hydrolyze our ester. So the ester bond also is hydrolyzed. Again, the OH goes to the C double bond O, and the H goes to the oxygen for an ester. And so your 2 amino acids, you have your NH2CH, and you got your R group being this carboxylic acid, acidic amino acid. And then you have your other one, which is NH2, your phenylalanine. So your CH2 with your benzene. And your C double bond OH. So there are the 2 amino acids that you get when you hydrolyze aspartame. All right, so draw the structure of another dipeptide that could be prepared from these amino acids. And so basically, we're going to put our phenylalanine first and our aspartic acid second. All right, so it's a different primary structure. The primary structure is the sequence of your amino acids. All right, so this time we're going to put the other one first. You got your CH, CH2 with your benzene ring. All right, and then your C double bond O, we're going to lasso water. We're going to lasso the OH here with the NH here to form our peptide bond. And so now we have NH. And now we have our carboxylic acid, CH2, C double bond O, OH. And then our C double bond O, OH. All right, so this is our dipeptide. So a dipeptide means 2 amino acids. All right, but it also means 1 peptide bond. All right, so that is also a very simple question to miss. A dipeptide has how many peptide bonds? Well, most people will put 2. That is the wrong answer. A dipeptide has the 1 peptide bond, and that is this bond. So this bond can be called a peptide bond, or the same thing is an amide bond. So call it either one, peptide bond or an amide bond. All right, this bond is always an amide bond. It's only a peptide bond when you bring two amino acids together. All right, so the next part says, how many tripeptides can be made from amino acids, valine, and alanine? So I'm just going to use V and A. All right, so you could have 3 valines, you could have 3 adenines, alanines, and so then you could have 1 valine, 2 alanine, and so of course that V could go in the first one, or the second one, or the third one. So these are all different primary structures. Well, we could have 1A and 2 V's. So the A could go at the beginning, the A could go in the middle, the A could go at the end. All right, and so there are 8 tripeptides that you could make from these amino acids. Now, if it said it had to contain both of them, well, then your answer is 6. But you could have all 3 be the same thing, according to the way I'm reading this one. All right. Let's go here. Backwards on this one. That. All right, I'm going to go through a little bit of the polymers made RNA and DNA. Make sure that you can easily tell the difference between RNA and DNA. All right, so RNA and DNA, these are both polymers, and the monomers are nucleotides. All right, so this one's not showing whether it's RNA or DNA, but we're looking right here to tell the difference between RNA and DNA at the 2' at the sugar. If there's an oxygen there, you've got RNA. If there is not an oxygen, both of those are hydrogens off that carbon, then you have DNA. All right, and so of course a nucleotide, you have to know that it contains a ribose or a deoxyribose, depending on RNA or DNA. Off of 5' you have a phosphate, and off of 1' you have a nitrogen base. All right, and of course the 5 bases, that's your C, T, U, A, G. Interesting to note that the only structural difference between thymine and uracil is a methyl group. So there's a methyl group off of this carbon in thymine. It is a hydrogen off of that carbon in uracil. That is the only structural difference between those two nitrogen bases. And the purines are the single ring, and the pyrimidines are the pyrimidines, the longer word, is the 1 ring, and the purines are the 2. So your pyrimidines, I'm not going to ask that, purines, anyway. So if it's a 2-ring system, it's a purine. If it's a 1-ring system, it's pyrimidine. All right, so you're again looking right here to see if you have RNA or if you have DNA. So that is the only spot that you should be looking at to see if it's RNA or DNA. The 2' carbon, if it has an O, then it's RNA. If it doesn't have an O, it's DNA. And the reaction to get the phosphate on there, so it's again, a lasso of water. You take the OH from your phosphate and your H from your 5' hydroxy, and this forms your nucleotide. So nucleotide, again, you've got your nitrogen base off of carbon 1, you got your phosphate off of the 5' carbon, and this tells you that we are looking at a DNA. All right, there is no oxygen listed off of carbon number 2. So this is a monomer of DNA. So again, the only way you would know RNA versus DNA, you're looking right here. If it's got the OH, then it is it's RNA. If it has an H, then it is the DNA. It's the deoxy. All right, so here, again, I'm not going to have you name these things. You don't have to know the bases. Right here, all I'm going to ask is this RNA or DNA? And this is RNA because your 2' carbon has an oxygen. All right, again, that is your RNA, and that's the name of it. All right, so now when you are going to link these to make the polymer, you're going to link it, and then I will always put an OH here for my phosphate, because to link your ribonucleotides, the monomers of RNA and DNA, is you take the H from the 3' hydroxy and the OH from the 5' phosphate, and that's how you link it. And so when you link that here, we have made this bond. All right, so when you link these two different nucleotides into a polymer, you made this bond. Now, it's called a phosphodiester. So remember your esters from organic. That is an ester. All right, here's your ester. A phosphorus ester would be a P double bond O with an OR. All right, a phosphorus diester would mean that you would have to have an OR on the other side as well. And since it is a phosphate, then it is PO4. So anytime you have a P double bond O with an OR on two sides, OR here, that's why it's called a phosphodiester. It is a phosphorus with two ester groups. All right, and so this is DNA. They're not showing any oxygen here, so this is your DNA. All right, so this, of course, you have the OH here, so this is a strand of RNA. And of course, you would know that if you looked at the very front and said RNA, or right here where it says RNA, or here where it says uracil. All right, so lots of reasons to know that this is RNA. But again, you are making this polymer by lassoing water from your 5' phosphate and your 3' hydroxy. So it is always a 5' phosphate that's going to lasso water with your 3' hydroxy. That's how you link your RNA and your DNAs together. All right, so again, here's DNA. Again, you can see DNA by only H's here. You can see DNA by thymine here. You can see DNA because it labels it at DNA a couple of times. All right, but this is DNA. But they are, again, it is the 5' phosphate that you're going to lasso water with the 3' hydroxy. That's how you make your polymer for both RNA and DNA. All right, so we talked about the adenine, thymine, only having two hydrogen bonding, and that's why they have the two dashes. All right, there it is, showing the two hydrogen bonds between your adenine and thymine. And then your GC, your guanine, cytosine, this has the three hydrogen bonds, and we show the three hydrogen bonds there. And of course, three hydrogen bonds is a much stronger interaction for the GC than the two hydrogen bonds connecting the A and the T. All right, and so you have your double helix, and that is all based on the hydrogen bonding from the base pairs. All right, and so they show the two lines here showing the two hydrogen bonds between all T and A, and then they have the three hydrogen bonds being shown between all the G and the C. All right, and so again, if you are reading the question, it's a very simple question. Now we're going from DNA to DNA. You got to know if you're going from DNA to DNA, or if you're going from DNA to messenger RNA. All right, and so right now we're just writing the complementary base sequence for the matching strand in the following DNA section. We're looking for a DNA. So you have to know GC, you have to know TA. So here's A, this is T, G, C, T, A. CG, CG, AT, AT, TA, and CG. All right, so it should be a very, very simple problem. All right, and so that's how DNA replication works. You're going to bring in the base pair is going to line up perfectly. So you have the parent strand, it's going to separate, and you're going to get two identical strands called the daughter strands. And that is just DNA replication. Fair enough of that already. Let's see what else we got. Oh, we didn't talk about that too much. All right, let's talk about enzymes. I know we've got it a little bit more. All right, so you got your proteins. That's that. You know your alpha amino acids. Again, when you talk about polar, non-polar, you're talking about the side chain R. Again, here's the neutral form. This is always neutral form, but the ionized form showing the two different ions are called the Zwitterion form. Glycine is the only non-chiral amino acid, and so it's the only one that doesn't have an L in front of its name because it is not chiral. It has two hydrogens, and that carbon is not chiral. For the other 19, the carbons are all chiral. The naturally occurring amino acids are all L, which means the NH2 is on the left. So when you're writing L-alanine, and you have it here, you've got your carboxylic acid group on top. You've got your NH2 group on the left. Ugly N, that is an NH2. You got your H here, and then you got your 20 different R groups here. All right, but for your alanine, that is the R group CH3. The reason why, of course, it's not L-glycine is because it's not a chiral carbon. All the others, 19 of them are chiral that are of the main 20, and one is not. And the one that's not is your glycine. All right, and so we're going to talk about non-polar and polar side chains. All right, so your polar side chains are going to have an oxygen. If you have an oxygen, your side chain is polar. If you only have carbons and hydrogens, your side chain is non-polar. If you have a carboxylic acid group, you're going to have an acidic amino acid. as you do in aspartic acid. If you have an amine group, you're going to be a basic amino acid as you have in lysine. All right, and so you have your nonpolar, so that's H. Here's C and H only, 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 here's C and H only. All right, here's C and H only. All right, now there are two, and we did this one in the homework, methionine. This is a sulfur between two carbons. That one's nonpolar. The other one is going to be harder to remember because it looks like an amine. It does look like an amine. And when you take organic, you'll know that these electron pairs are not available to attack any hydrogen because they're part of the pi system, making this aromatic. So anyway, so tryptophan is a neutral amino acid. And note, they give the neutral pHs, all right? And those are all around 6. Here's a 5.5 and a 5.7 and a 6.3 and a 5.9, all very close to 6. And so you have your isoelectric point. They are completely neutral at a pH of 6. All right, and so here is polar, has an oxygen. Here's polar, it has an oxygen. Here's polar, it has an oxygen. This one was in the homework. This is our cysteine, right? And so that one is polar. The SH is polar. This one has oxygen, is polar. Oxygen, polar. All right, so if you have oxygen, then you have a polar side chain. All right, and all of the acids and bases are polar, so these are all polar. All right, but you have your aspartic acid, glutamic acid. Note that those are right at a pH of 3 for them to be neutral for the acids. All right, and then your 3 basic amino acids. This one has 2 nitrogens. Actually, one of those is not basic at all, but the other one is. One is part of the pi system, making it aromatic. The other one has the electron pair to attack a hydrogen. All right, and so again, the pH is not much greater than 6, but it is greater than 7. And so this is a 7.6, this is a 9.7, this is a 10.8. All right, so the pHs of your bases are much, have a bigger range than the acids are all both right at 3. All the neutral ones are right at 6. Your basic ones are just, this one, your histidine is just barely above 7. All right, your lysine has an amine group, and then you have 3 nitrogens on your arginine, which has a pH of very much the highest at 10.8. All basic and acidic are polar R group side chains. All right, so if you're just going to identify as polar, nonpolar, H, nonpolar. This has an oxygen on the side chain, polar. That's all you're looking for. That gets you the answer right 15, 16 out of 20 times. All right, again, the naturally occurring amino acids are the L, which means the NH2 is on the left of your chiral carbon, written in a Fisher projection with the carboxylic acid on top. Again, if you take the mirror image, then you would have the NH2 on the other side, and that would just be the D form. And the D form is not naturally occurring, easily made, but not naturally occurring. All right, same thing here. You just take the mirror image. Of course, your side chain is CH3, that's nonpolar. Your side chain here is the one in the homework, your cysteine, and your SH is a polar side chain. All right, zwitterion just means a dipolar ion. Again, here is your acid, here is your base. You do an internal acid base. You put the plus charge on the N, negative charge on the O. You have a neutral but dipolar zwitterion. And this occurs at the isoelectric point. All right, for a neutral amino acid, that's where the pH is equal to 6. If you're an acidic amino acid, the pH is 3 at the isoelectric point where it is no overall charge. And the base has a big range. I just averaged it and said 9 for the pH for the base. All right, So again, if you have your amino acid and you stick it in base, you're going to pull off another hydrogen. So in base, your overall charge is going to have a -1 charge. If you stick it in acid, we've already done this, then you protonate the negative, and now your overall charge is positive. And these are for the neutral amino acids, and so usually you're at a pH equal to 3 here, and in the base you're at a pH equal to 9. All right, so yeah, again, so you have your neutral, so your pH is equal to 6. That's your your neutral pH, low pH. So again, lower than 6, go down to say 3. High pH, go up to say 9. Is my numbers. I like going by threes. It makes it easy to remember, and it does work. All right, so you can separate them by different techniques if you know the charges. All right, so alanine pH above, so that means a high pH. So you have to know high pH means base, and that means it's going to have a negative charge. Alanine at low pH, that means acidic. Low pH is acidic, and it's going to have a charge of plus. And so, of course, this one has a charge of plus, this one has the charge of minus. All right, and the side chain is a methyl group that is a non-polar side chain. All right, so again, your peptide bond is an amide bond. All right, so last week, way too much stuff, but you lasso water. Now, if you write it in its Zwitterion form, then you got to take 2 H's from your NH3 with the O here in order to get it. I prefer it to be in the neutral form, just like with my phosphate. I like that to be an H. I like this to be NH2, and I like to lasso the OH and the H. But regardless, it gives you your peptide bond. All right. All right. Here we have a polar side chain. We know that because it has an oxygen. This also has an oxygen, also polar. All right, we're going to lasso water. When you lasso water, this has 3 H's on it. All right, so you lasso 2 of the H's. Again, I like to put OH here and H there. Anyway, you're making your amide bond. You're going to have your C double bond O, N with an H. That is your dipeptide. You're going to have your dipeptide having 1 peptide bond. Your dipeptide has 1 peptide bond. All right, so 2 glycines and 1 alanine. Again, we had this when I did the A, and B, same type of thing. All right, so you can end with that one. You can put that 1 in the middle. You can put that 1 at the beginning. You have 3 different possibilities when you have 2 of the same amino acid and 1 that is different. There are then 3 possible tripeptides that you could form. All right, now when you have 3, L, G, and A, all right, so you could have L at the beginning, you can have L in the middle, you can have L at the end. All right, so you're going to end up, and the formula is 3 with the exclamation point. I know what that says. Anyway, it's 3 times 2 times 1. Factorial. That's 3 factorial. All right, so we know that we are looking for 6. So you can have then the L at the beginning, all right, but then you could switch the A and the G. The L in the middle, but you can switch the A and the G. And then the L at the end, but you could switch the A and the G. All right, and so there are your 6 possible tripeptides. And again, your tripeptide, tri means 3 amino acids, and that means 2 peptide bonds. All right, so if you get this, it's just going to say polar, nonpolar. That is nonpolar. Polar or nonpolar. All carbons and hydrogens, nonpolar. Cysteine for the third time is polar. Methionine for the third time is nonpolar. All right, so when you have the S between two carbons, it's nonpolar. If you have SH, then it is polar. All right, and so it could also say what kind of peptide is this? Well, it says that tetrapeptide because there's 4 amino acids, and it has then your 3 peptide bonds or amide bonds. The amide bond there, there, and there. 3 amide bonds. All right, so your primary structure is just a sequence of your amino acids. So again, when you had 3 different ones, you had a possibility of 6 different primary structures. And of course here, if you go here, there's 4 different, so you would have 4 factorial. So that's 4 times 3 times 2 times 1. So you'd have 24 different primary structures for a tetrapeptide where you had 4 different amino acids. All right. Hydrogen bonding. So you have your secondary structure, and that's when you have your hydrogen bonding. And that again is your alpha helix with hydrogen bonding or your beta pleated sheet. Your secondary structure is all about hydrogen bonding. Okay, you can also have the triple helix. All right. Essential amino acids, these are the ones that must be obtained from your diet, so they're not synthesized by the body. So this is important if you are a vegetarian to make sure that you get all of your essential amino acids. Meat and dairy, these are complete proteins. They have all of the essential amino acids in them. But vegetables are missing 1 or more. So make sure if you are a vegetarian, you're getting all of your amino acids that you need, your essential amino acids. All right, tertiary structure is the overall 3-dimensional shape of your protein. All right, and they are determined by your attractions and repulsions between your side chains of your amino acids. So your acids and bases, acidic and a basic amino acid, they will form a salt. You've got your nonpolars and nonpolars that will interact. You got your polars and nonpolars repelling. All kinds of interactions between your side chains. All right, so hydrophobic interactions. So these are your nonpolars. Hydrophilic interactions. These are your polars. Salt bridges. That's your acid and base. And then hydrogen bonds, OH, NH. And then your disulfide bonds. This is your cysteines. So you can oxidize your cysteines and get your disulfide linkages. All right, so you got your globular proteins. You got your fibrous proteins. All right, so again, so primary, secondary, tertiary, quaternary structures. So when we're talking about these, primary is just the order of your amino acids, the sequence that they come in. If you did the 3 that we did the first time, you could have 6 different primary structures. If you had 4, we had 24 different primary structures. So it's a sequence of your amino acids. Your secondary is all based on hydrogen bonding. So secondary structure, hydrogen bonding. So it's the normal ones are the alpha helix or the beta pleated sheet. The triple helix is also another possibility. Your tertiary is the folding of the protein into a compact 3-dimensional shape, right? And these are interactions between your side R groups. So you have your 2 nonpolars interacting, your 2 polars interacting, your acids and base reacting to form a salt. And then your quaternary structure is simply the combination of 2 or more protein subunits that form a larger biologically active protein. All right, so you should be very familiar with primary, secondary, and somewhat familiar with the tertiary and quaternary. All right, so beta pleated sheet. So that is your secondary structure, order of amino acids. That is your primary structure. A protein with 2 or more peptide chains. All right, so now you're talking the quaternary structure. You got multiple peptide chains. The shape, that's your tertiary. Disulfide between R groups, that could be one of two. That could either be tertiary or secondary. So they have it as a tertiary for your disulfide bonds between R groups. When you're talking about R group interactions, you're talking about tertiary, but many people will put the disulfide linkages as a secondary. Denaturing your protein, you can heat it, acids and bases, just breaking up the structure, agitating. All right, so enzymes. So I think we covered this, but if not, the key thing for an enzyme is it is a biological catalyst. So your normal reaction profile has a very high energy of activation. When you add an enzyme, that is a catalyst. It lowers the energy of activation and it makes the reaction much faster. And enzymes are proteins. So you need to know that enzymes are proteins and they are biological catalysts. I think we all know that, but a reminder, do not get the easy questions wrong. Know what an enzyme is. And you can easily identify an enzyme because the name ends in ACE. So if you want to catalyze a reaction of sucrose, well, you use sucrase. Lock and key, not going to ask that. So enzyme is just, you need to know that an enzyme is a protein and it is a catalyst, which means it lowers the energy of activation. Don't need to know any of that. All right, so that's just the basics of enzymes. Protein, biological catalyst. All right.